Hello everyone, this is Sudhanshu Sarkar, Assistant Professor, Department of Electrical Engineering, Narula Institute of Technology. So today I'm going to discuss a topic on circuit theory and network. So the lesson plan of circuit theory network is given here. So I have to cover total 4 modules. The first module is the introduction, then network equation, then coupled circuit and Laplace transform. So today I'm going to talk about the coupled circuits. That is in module 4. Total I have 2 lectures from this section. Now let's start to talk, but before that I'm just showing you the course outcome of the circuit theory network. So total 5 course outcome of this particular subject, and the topic of coupled circuit, that is, or you can say the magnetically coupled circuit, is in, we can say it in CO1, or we can consider it as CO in CO5. So magnetically coupled circuits. So, or you can say it's a coupled circuit. So coupled circuit, I'm going to talk about these two particular topics, that what is self-inductance and what is mutual inductance of coupled circuit. So the objective of this lecture is basically to understand the basic concept of self-inductance and mutual inductance. Then the second objective of this lecture is to understand the concept of coupling coefficient, and dot determination in circuit analysis. This is the total objective of this particular subject, but today in this chapter I will discuss only on the first objective, that is the basic concept of self-inductance and mutual inductance. So let's talk about what is self-inductance and what is mutual inductance. So self-inductance, mutual inductance, we already talk on this topic from first semester, that what is inductance, what is capacitance, what is self-inductance, what is mutual inductance. So on this topic we already talk several times. So here the self-inductance is very important part, and also the mutual inductance. With the help of these two types of inductance, we will develop the coupled circuit explanation. So now at first, the self-inductance. When two loops with or without contacts between them affect each other, the magnetic field generated by one of them is called magnetically coupled. So you can say that this is the definition, we can consider it as the coupled circuit definition. So when two loops, so here two loops should be there. Look, the important part I'm just marking here. When two loop, there should be two loop. In that, without contacts, this is the important part. Between them affect, they will affect each other. The magnetical field generated by one of them it called magnetically coupled circuit. Example, transformer. This is a very good example of a coupled circuit. So why it is good example? Because transformer has two sides, one is primary, one is secondary. So the power entered from the primary side and its exit from the secondary side. So here the working principle, if you follow the working principle of the transformer, then you will find the magnetic field will generate inside the transformer. There are two loop, primary, secondary. There is no contact between primary and secondary. So the transformer is an ideal example of a magnetically coupled circuit. Now, an electric device designed on the basis of the concept of magnetic coupling. The basis of the concept of magnetic coupling. Look, used magnetic coupled coils to transfer energy from one circuit to another. So these are the basic and fundamental idea from coupled circuit. An electric device designed on the basis on the basis is repeated here, so we can neglect this part. An electric device designed on the basis of the concept of magnetic coupling. On the basis of magnetic coupling, we can design the electric device. And then second one is used magnetically coupled coil to transfer energy from one circuit to another. So using these magnetically coupled coils to transfer energy. So what do we transfer? Transfer energy from one circuit to another circuit. So this is the important part. So this is actually the concept of magnetically coupled circuits. Now move to the next slide. So here I'm going to discuss about the self-inductance and mutual inductance. Self-inductance. Only the self-inductance part will be discussed in this slide. It is called self-inductance because it relates the voltage induced in a coil by a time varying current in the same coil. So why it is self-inductance? Because it relates the voltage induced in a coil by time varying current in the same coil. So for that reason, same coil, the term, this term is the most important term for the self-inductance. So what is happening? It relates the voltage induced, the voltage which is inducing inside the circuit, it relates the voltage induced in a coil by time varying current in the same coil. If it is in the same coil, then it is called the self-inductance. The next one is consider a single coil with, so here we are considering a single coil with n number of turns. Single coil with n number of turns. When currents small I, so look, consider a single coil. A single coil we consider with n number of turns. Suppose 1, 2, 3. If we consider this is n number of turns, when current small I flow through the coil, a magnetic flux phi. So a magnetic flux phi is generating here. A magnetic flux phi. This is the phi is produced around it. So what is happening? We are considering a single coil with n number of turns. Maybe it is 4, 5, 6, 7 or 100 number of turns. So we are considering for the generalization of the circuit that the number of turns is n. When currents I small I, this current is actually flowing with time t. When current I flows through the coil, if it is flowing through this coil, the magnetic flux, what? The magnetic flux, this magnetic flux phi, this is phi, is produced around it. So some magnetic flux will produce around this coil, a number of turns coil. So this is actually the self-inductance. Now, we can clarify this part also with the help of some equations. According to, so we can say, according to Faraday's law, so what can we do? According to Faraday's law, the voltage V, if we consider the voltage is V for this case, so what will happen if we consider the voltage V, this V, according to Faraday's law, according to which law? Mark the important lines. Faraday's law, the voltage be inducing in the coil is proportional. This part, remember, is proportional to n number of turns, capital N number of turns, and the rate of change of magnetic flux phi. Look very carefully. What Faraday's law is saying or explaining, the voltage V induced in the coil is proportional. That means V is proportional to number of turns N and the rate of change of magnetic flux. The rate of, this is the important, rate of change of magnetic flux. So what is flux? Someone tell me what is flux? Flux is, we consider flux is the phi. So what will be the rate of change of flux? So if we write d phi dt, then it is called rate of change of flux, d phi dt. So now again move to the definition. According to the Faraday's law, the voltage V induced, okay, in the coil, very good, is proportional. That means according to their and the rate of change of flux. So we can say that V equals to N d phi dt, rate of change of flux. D phi dt, d phi is the flux and t is the time. So rate of change of flux means d phi dt. This is, we are considering this as our equation number 1. But the change in the flux phi is caused by a change in the current. So why this flux is changing? Flux is actually changing with a change in current. That means we can explain this d phi dt. It has some, because look, but the change in flux phi, change in flux phi is caused, why? It's caused by a change in current I. So we can write this like this way, d phi dt equals to caused by change in current I, d phi di into di dt. Okay, so remember this part. Why this is happening? This one. Because the change in flux phi is caused by change in current I. So that we can modify the equation d phi dt in the form of d phi di into di dt. Now, please remember this equation for the better understanding of self-inductance. Thus, in equation 2 into 1 else V equals to N. So we are replacing here d phi dt with d phi di dt. Question number 3, just to prove this. Then you can say that V equals to L into di dt. L into di dt. So why L? Because we know that L equals to d phi di. So we are just replacing L equals to d phi di. So V equals to N into d phi di. So to the previous slide. What is this? Yes. So from equation 3 and 4, the self-inductance L is defined. So why it is defined? Because we consider here L equals to N into d phi di. So we just write L equals to N d phi d, sorry, di dt. So it is d phi di dt, d phi dt. From equation 3 and 4, self-inductance L is defined as d phi di dt. No, d phi di. This should be d phi di. So V equals to N into d phi di. L equals to N into d phi dt. Del di dt. So L is obviously equals to N into d phi dt. D phi di, not dt. This will be I. Let's rewrite this. Okay, there is no problem with this part, but here we have to change. It is written wrongly. This will be d phi di, because L equals to, if we consider equation 3 and 4, if we compare, then L equals to N into d phi dr. So that part we write here. So for the clarification, I just write. So it's a mistake. So this should be I. So L equals to N d phi di. Now move to the next slide. So in this way, we can find the self-inductance. So after finding the self-inductance, now we can talk about the mutual inductance. So what is mutual inductance? When two inductors coils are in close proximity to each other, magnetic flux caused by current in one coil links with the other coil, therefore producing the induced voltage. Why induced voltage is producing? It has some reason. Two inductor coils are in close proximity, okay, each other. Magnetic flux caused by current. So for current, the magnetic flux is causing in the coil links. What is happening? Links with the other coil, therefore producing the induced voltage. So for that reason, the induced voltage is producing. Fine. Now mutual inductance is the ability of one inductor to induce the voltage across a neighboring inductor. So mutual inductance is the ability of one inductor to induce a voltage across a neighboring inductor. I think it is clear now to all of you that what is actually the mutual inductance. Now consider the following two cases. Case 1, following two cases. So here, considering the following two cases, TWO, considering the following two cases, yes. So what can I say? Case 1, two coils with self inductance L1 and L2, which are in close proximity with each other. Figure 2. Coil 1 has N1 turns while coil 2 has N2 turns. So in case 1, what is happening? So in case 1, self inductance 1 is L1, this is L1 of this first coil, self inductance L2, which are in close proximity. They are in close, very close proximity. Look, this part. How can we show? We can show these like this is in close proximity with each other. Figure 2, as per figure 2, coil 1 has N1 turns. We are considering that this coil 1 has N1 turns. Coil 1 has N1 turns and coil 2 has N2 turns. Okay. So what can we do for this? So please try to remember that L1 and L2, which are in close proximity with each other. Figure 2, coil 1 has N1 turns while coil 2 has N2 turns. It's very clear to all of you. N1, N2. This is L1, this is L2, close proximity. Now, the magnetic flux phi 1 from coil 1 has two components, phi 11 and phi 12. Go to the last slide. So what is in the last slide? L1, what is it L1? So phi 1, magnetic flux phi 1 from coil 1 has two components, phi 11, phi 12. So it has two components. One is phi 11, one is phi 12. Look, these are the two components. Phi 11, phi 12. Okay. So phi 11 links only coil 1, phi 12 links both the coil. So phi 11 links only coil 1 and phi 12 links both the coil. Look, this is linking. Phi 12 is actually linking coil 1 and coil 2, but phi 11 is only linking with coil 1. Hence, we can say that phi 1 equals to phi 1 plus phi 12. Hence, we can say phi 1 is equals to phi 11 plus phi 12. Question number 6. Thus, voltage induced in coil 1. V1 equals to N1. We already defined. Phi 11 di1 dt. That means this is L1 L1 di1 dt. Question number 7. Now, voltage induced in coil 2. We have to calculate this part also. Voltage induced in coil 2. So V2 for coil 2 it is N2. So phi 12 is linking between coil 1 and 2. So it is phi 12 divided by d phi 12 phi d12 di1 dt. So that is actually M12. This is the mutual inductance. So what is mutual di1 dt? So what is M12? M12 is the subscript 21 in M21 means the mutual inductance on coil 2 due to coil 1. Yes, it should be 2-1. This is not 1-2. Here, change. So in this slide, look very carefully. V2 equals to M2 d phi 1 2. This is the flux between the two coil di1 dt equals to M21 di1 dt. So why it is 21? 21 is subscript 21 in M21 means the mutual inductance on coil 2 due to coil 1. Coil 2 due to coil 1. I think it is clear now to all of you. Previously it was wrongly written. So this part N2 d phi 1 to di1 equals to N2 1. 1 means the mutual inductance on coil 2 due to coil 1. Okay. So this way we can find the voltage V2. Now case 2. So case 1 is complete. So now let's discuss on top of case 2. So in case 2, same circuit but let current I2 flow in coil 2. Same circuit but I2 in flowing in coil 2. So the magnetic flux phi 2 from coil 2 has two components. The magnetic flux phi 2 from coil 2 has two components. One is phi 2 2 and second one is phi 2 1. Links both the coil. Then we can say, what can we say from this definition? We can say that phi 2 is equals to phi 2 1 plus phi 2 2. Phi 2 is equals to phi 2 1 plus phi 2 2. Same as before. The last one. Go to the next slide. Thus voltage induced in coil 2. So what will be the equation? V2 equals to N2 d phi 2 2 di2 di2 dt. So here d phi 2 2 di2 equals to L2. No problem with this. We already derived, proved this one in previous slides. Equation number 2 and the voltage induced in coil 1 for this case. So V1, what will be the value of V1 for this case? This should be N1 d phi 2 1 di2 di2 dt. So what is this? N1 d phi 2 1 di2. This is M21. The previous case it was M12. Previous case it was 2 1. So here subscript 1 2 in M12 means the mutual inductance on coil 1 due to coil 2. Mutual inductance in on coil 1 due to coil 2. I think it is clear to all of you now that what I am going to explain or what I am trying to say. So look, so here let me erase this part. So here it was phi. So first is find phi 1, that is 1 1 phi 1 2, then V1, then V2. Okay, so V2 for V2 it was M21. That means 21 means the mutual inductance on coil 2 due to coil 1, and here phi 2 2 equals to phi 2 1 and phi 2 2, that is phi 2. So phi 2 is the summation of these two, phi 2 1 plus phi 2 2. Next we find V2, the voltage, the second coil, and the voltage induced at coil 1. On that case, when V2 is active, then what is happening? V1 equals to N1 d phi 2 1 di2 di2 dt. So M12 di2 dt. So what is M12? 12 subscript 12 in M12 means the mutual inductance on coil 1 due to coil 2. Since the two circuits and two currents are the same, two circuits and two currents are the same. Look, two circuits and two currents are the same. That means we can say that M21 equals to M12. That is equals to M. So that's all about the first part of couple circuit. So now I use a few internet sources to develop this PowerPoint presentation, and the circuit theory book of Abhijit Chakraborty is also used to develop this book. But but my mistake, I failed to mention the reference of that particular book. Now, thank you for watching this lecture. Thank you, everyone.